In order to begin our discussion of the resident conditions of a laser cavity, we start with our YNU ray trace equations from linear optics. If we convert this into matrix form, we find that depending on the element, there is a matrix ABCD times an initial ray height and angle, which will give us the output ray height and angle. If we take the case of a linear laser cavity such as this, composed of a flattened curved mirror, and expand this into a lens equivalent system, we find that the total matrix is equal to the product of each individual matrix, which is equal to ABCD from above. The monochromatic coherent light in a laser beam cavity can be characterized by Helmholtz wave equation. After rigorous math, we find the following equation for a Gaussian beam relating the complex beam parameter Q to its radius of curvature, wavelength, and spot size. The following equation relates the complex beam parameter before and after a system to its ABCD matrix. In order for a cavity to be in stable resonance, the complex beam parameter before and after the cavity must be exactly the same. Q is equal to Q prime. This results in the following equation, which you might notice is in the same format as our equation for a Gaussian beam. From that, we are able to extract relationships for W and R. In order for a cavity to be stable, W must be a real value for an ABCD matrix. This means that the absolute value of A plus D must be less than 2.
This is the energy diagram of our gain medium. What's happening is we're exciting an electron in our helium to create a metastable state. That metastable helium then collides with our neon, transferring its energy. The neon then begins to relax to one of these states, releasing a photon. Any relaxation after that to the ground state is non-radiative. This will continue to happen until we have an inversion of population in the neon, resulting in positive gain. We can control our dominant wavelength via our tube length, wavelength reflectivity of our mirror, and ratio of helium to neon inside the tube.
In order to understand the angular dependence of the reflectivity of a thin film stack on a mirror, we must first consider the simplest case. In order to determine the reflectivity, we need to find the phase difference between the first and second reflections, which is given by the following equation. In a multi-thin film coating, the reflectivity can be calculated with the following three equations. For light at normal incidence on a quarter wave layer, the matrix simplifies to the following. At an angle where the effective path that the light travels becomes a half wave layer, the matrix simplifies to the identity matrix. When the angle is changed even farther, so that the path becomes 3/4 a wave, we simplify to the same as in the case of a quarter wave, and therefore we see an oscillation in the reflectivity with respect to angle.
This is the V cavity that we attempted to make in lab. To begin aligning the system, we first aligned a linear cavity using our gain medium faced towards the fold mirror. Afterwards, we aligned a green laser along the other arm of the cavity to become a reference beam. Then we aligned the final curved mirror on the other arm in line with the green laser. Once that was done, we removed the curved mirror in our HeNe linear cavity to finalize the laser. This was the best method for aligning the V cavity because the fold mirror is only highly reflective at 635 nanometers. Additionally, the beam width of the linear HeNe cavity was too wide for us to use after the fold mirror. However, due to a high amount of loss in the system relative to the gain medium, we were unable to get the system delays.
The following graph shows the angular dependence of the reflectivity of our fold mirror. We were illuminating about a 15-degree angle, which would result in about a 60% reflectivity. Clearly, the amount of loss we have in the system is much more than the gain, and therefore we didn't laze. Because we were not able to get the V cavity to laze, we took a little bit of data of the beam waste of a linear cavity in order to test the stability regions. We found our data points to be accurate, but not necessarily precise, which suggests an experimental error.
When taking measurements of the linear cavity at short cavity lengths, we were noticing that we got higher order modes due to misalignment, and here are some pictures of what we were seeing.
The application of V cavities is seen in second harmonic generation in a laser in which the fundamental beam is completely reflected by the mirrors. However, the second harmonic, which is half the wavelength of the fundamental, is transmitted through the fold mirror.